Okay, I think we'll get started. So today we're going to wrap up the mini-series and go through some examples, look at the website for this course, and work on the software program, a chance to explore some of these ideas that make it a little easier than writing everything out by hand, because sometimes we want to get a number of terms out there before we can see a pattern. Okay, so we'll start here with just looking at a specific example. Let's say we're targeting the number 52, and we'll look for the number of partitions and distinct partitions of the triangle numbers, or by the triangle numbers, in 52 for m equals 3, m equals 4, and m equals 5. Okay. All right, so for now, just ignore this. These green, and let's look at how we might construct 52. Well, the brute force approach would be to consider all the triangle numbers up to or less than 52 as your feedstock for putting these together. Wouldn't make sense to carry any triangle number that's bigger than your target along. And then you look for all the representations, or if we're working by hand, we would probably go directly for partitions and not write down all the different orders. So when we do that, we arrive at 5 partitions, and then as we look at them, very easy to pick out by eye which ones are have repeats. And so the distinct partitions here would be 4, sorry. And we'll go through in our software and try to pick these up as well. So we'll come back to this number 52 as our example in the software. Okay, well, now let's go to m equals 4. And for m equals 4, of course, 0 is in the set, and that's important. It's easy to forget about 0, but 0 is in the set, first member of the set, and we want to, so just ignore this last 0. We would add this column of zeros as new partitions for the for 52, because we're just these already add up to 52, we're just adding 0. So from that, we have these original 5 and 4 respectively, but now ignore this green over here, just look at these 4 numbers here. We have the opportunity to build the number 52 with more flexibility because we have 4 to work with. And look at this one here, 1, 6, 4, 5. Well, we could break that 6 now into 2 3s, 1, 3, 3, 4, 5. And so we get an additional 5 more. So our total partitions is equal to 10. But 3 of these are repeats. So here's a repeat, here's a repeat, and here's a repeat. And so we get 2 additional and 4 up here. So we have 6 total for m equals 4. And now let's look at m equals 5. We've got all of these by simply adding 2 zeros here. And of course, that'll make these all repeats and zeros here. So that these 10 we have already, and then we have that additional degree of freedom here, so we can get a number more. In fact, we get 10 more, but in all cases there are repeats. So we have a total of 20, these 10 and these 10, but all of these are repeated, and also these, now we have 2 zeros, so all these gets wiped out. So we're down to just 2 distinct. Okay. All right, well, let's go to the software, go to the computer. We'll work with some of the software, and then we'll come back and look at two famous theorems, Gauss's Eureka theorem and Lagrange's four-square theorem. So we'll jump over the computer now. All right, so here we are on the computer. So let's go ahead and go to our web page. So you can just search my name, and it's darrenolness.com. So we'll go there. And then this is under Learning Communities GNL project. So let's click that. And this is still quite under construction here. So not the greatest, hopefully, but when you're looking at it, it'll be better. But we can at least get to our page for this course. So this is the group theory integer partition. And we are, of course, working through the paper that my students wrote. That's our group theoretical approach to partitioning of the integers. And first thing we can see here is we've got a link here, and we've also got a link down here in resources. So let's go click on that. And this takes us to the Australasian Journal of Combinatorics. And this is an open source journal, so you can view this from wherever you are in the world. And so here's where you can get a copy of our paper. And then we can also look at a second paper, and this is what was this is the paper that inspired our work. And we can see here now that so although we talked about this in the introduction to this course, it makes more sense now. Equations 7 and 8 are just cases of our of what we've now accomplished through the course here. All right, and then for you here, the software either in Windows, Mac, or Linux. So just click on these and download those. And then if you want to work with the code itself, there's a lot to be desired with this program. It's just a sort of a basic explorer, as we'll see in a moment. So you can go to the GitHub repository here and look at the code if you would like, and modify it as you wish. Okay, well, let's open up our program here. And so it's Figure-8 Partition Explorer. And let's just go tab by tab, and we'll just look at some examples. So in all the tabs, there'll be a choice of the family. So we can go triangle numbers, square numbers, and centered polygonal numbers. If you choose centered polygonal numbers, which we haven't talked about in this course, but it is in the paper, then that comes with an extra parameter, k, that indicates the number of sides on that polygon. A centered polygonal number with 3 sides is not the same as the triangle number, and 4 is not the same as square numbers. Okay, then let's just let's see, what do we want to do here? So this is going to generate the series, and this will just be for the triangle number. So pretty simple here. We're generating the first 200. It's only going to show a few of them, and we can see here the power series for the generating function here, and we can see kind of the density of these triangle numbers spreading out as we would expect based on the formula as we go up in number. And then here we can, of course, see 0, 1, 2 is not a triangle number, 3 is a triangle number. So this is just picking up the triangle numbers. If we do this with square numbers, we can see that 2 is a square, or 1 is a square, 0 is a square, 2 and 3 are not, but 4 is, and then we'd go to 9 to get the next one, 16 for the next one after that. Okay, so that's pretty simple on this tab. Then this is for the group theory stuff, and so let's try 3. We'll do 3 and 4 here. I'll do 3 first. Now, it is upside down from the tables we've been working with. So here's the one, here's the identity or the one, all three fixed points on the bottom here, and then it kind of goes up compared to our table in the paper that goes down. And then it gives the psi term structure over here, and the parity as this is, so parity is the character for the sign configuration. So even is 1 and odd is -1. So we can get that from that. And then this is the size of the classes. So we are familiar from the work that we've done that the conjugacy classes are size 1, 3, and 2, and 3 is has the odd number of transposes. So it is got the -1 for the sign of the sign character. Okay, now let's go to this tab, and this what this is doing is this is going to actually partition. Let's see. Right, so this is, let's compute this here. So we'll choose triangle numbers, and let's do 3 for the sum. And this now is showing what we showed in the paper. So this kind of completes the term as well, and then it gives. So this is kind of filling out the connection to the table from over here. So not a lot of new from here to here, and then down here we get. This is just psi to the m, so this is just the number of representations. That's the number of representations. This is the number of distinct partitions, and this is the number of, this is the number of partitions. It's the number of distinct partitions. And I don't know why this has gotten spread out, but let's scroll down quickly to 50. Oh, we don't have 52 in here. Let's see. Well, we'll get to where we can choose a target number here soon. Okay, so that's this, and then this is a fun one here. This one we can plot. I'm going to remove the representations and just show the. Well, let me leave that on there, I guess. And if I just do triangle numbers, and I'm going to increase this to 200, well, I'll do 200, and I'll do 100 here. And we can see here's with m equals 2, m equals 3. I should probably have done that one. We can see the number of representations exceeds here the number of distinct partitions, the green, and the number of partitions, orange here. And we can increase this up. I think I set it up to 2,000. So it goes out to an exponent size of 2,000. Okay, something's wrong here. Let me plot. I'm gonna. There we go. It's not catching that last 0. And so we can see this here. I'm going to turn this off. Kind of, let's look at something sort of neat here. This is how we can do some exploration here. So here is for m equals 3, the number of distinct partitions and the number of partitions are not that different. I'm going to increase this here. And we can do a couple of things. This is just showing both of those. We can get the ratio. So let's look at the ratio of these. And we see almost 1 in many, many cases. And then the difference is fairly constant throughout. But now let's change this to m equals 4. And this, we'll see kind of an interesting trend here. This looks almost linear. So here, n equals 3. I'm going to redo that. Sort of a kind of a hook, maybe square root, and then 4 is linear. It's linear, and then if we go to 5, we're going to get some positive curvature, and we start to get more separation. So there's more degrees of freedom there, and as we saw in our example of 52. When we got up to 52, we had, that was a pretty dramatic example that had 20 partitions and only 2 distinct partitions. We bring this up to, say, 8. It takes a little longer to compute here, but we get a big separation. And we can plot the ratio. And I'm going to bring this back down to 3. So we saw that. Now let's go to 4. This was linear in the, so it's linear in the coefficients here, but this ratio is a little more, it's got this kind of heading to an asymptote. And then the difference, similar, although not so much asymptotic, but just growing. And we see here kind of an arc this way. So now let's go to 5 and return that back to coefficients. This showed that curvature here. Now let's look at the ratio, and this will be kind of hooked, and compute the difference, and we get more linear there. So fun to explore all these different possibilities, and you can do this, of course, with the square numbers as well, and see what happens there. See if the general shape stay the same. We see this variability increased a lot more. Okay, so that's this. Fun to explore this one. Oh, I should note here too, you can export to a file. I won't do that, but you just save that, and that'll export these data, so you can do more with it after that. Okay, last one, and this will connect with our target number here. So let's put a target number of 52, and then I don't think we need to. Well, we can leave this. This is a number of examples to list, and 20 is the highest it got, but let's just leave it. And triangle numbers here. So what this is going to do, this is something you can do to convince yourself of the formula. It will do a brute force, just numerical, find every combination that works. It just tests all the combinations, and if it equals the target number, it collects it, and then it'll use the formula. So we'll see a comparison of what the formula got and the brute force. So here the formula, here's the brute force count, and then a check mark for matching. And so this was with 52 with 3 numbers. Here's our 5 and our 4 that we saw, matches with the brute force. Well, we did brute force, and then there's the match. And we can scroll down. This is the representations. Here are the 5 that we have on the board, and these are the 4 that we have on the board that are not, that are distinct. Well, let's up that to 4. What did we see there? We saw that our total number went to 10, and our number of distinct went to 6. So let's do this check. 10 and 6. Again, we brute forced it. Here's our formula, and we, of course, match. And here are the ones that were on the board in both cases. And finally, let's go to 5, which is, we'll do a run of brute force, and there's our 20 and our 2. And our 20 down here, and our 2 here that were distinct. So a lot of the ones had zeros in them. Okay, we'll come back to this. I'm going to go to the board and look at some of those important theorems. All right, so Gauss in, it was 1796. I had mentioned that in an earlier video, then I doubted myself. Found what is called the Eureka theorem, and this is coming from what was found in his notebook, where he wrote the word Eureka when he proved that any non-negative integer, if you've got at least 3 triangle numbers, you can produce a representation. And we'll call it a partition, because as soon as you can produce one representation, you have at least one partition. So in the statement of theorem, it's usually representation, but for our purposes, I wrote partition there. Now, let's look at a couple of interesting sets here. Let's look at the set where m is equal to 1. So this is the m here. in that case, only the triangle numbers themselves can be partitioned by one triangle number. So that set is just the triangle number set. And then here's the Eureka theorem, right? This is the integers, right? Because every integer can be hit when m is 3 or more. But let's try 2 here. This is the only non-trivial set, because we know this is the triangle set, we know this is the integers. Here is, what are these guys? And we count out 1, 2, 3, 4, 5, 5 is missing in this set. And that's the first one that's missing. Looks like 8 is missing, maybe. I think I have that right. We'll check it here on the computer. So let's do a little problem. Let's see if we can find the integers minus this set. And so that'll collect all the ones that would be missing here, or the integers that can't be represented by two numbers. So let's give that a try. Okay, so let's go back to Coefficient Explorer here, and we'll set ourselves to triangle numbers, and we will set, let's see, I think that's all we need. So let's go ahead, and we don't need to compute 2000. This will go fast. Okay, and let's look now at the, not 3, or I had 5 here, 2. Right, we want to do two here. So 0, here's our n, here's our partitions. So we're going to look for the ones that are 0. So there's 5, 8, 14, and so on. So let's go ahead, and I'm going to shrink this down. And let's bring in the online encyclopedia of integer sequences, and let's type in the ones we find. So 5, 8, 14, 17, and 19, and 23. So let's try that. 17, 19, 23. Hopefully I didn't miss any there. And we'll search. And here we go. Numbers that are not the sum of two triangle numbers. And this is the series identifier. And we see here that these are what we found. So let's see. It says 50 isn't. It says 52 isn't. Okay, so let's try 52. 52. 52. It's confusing here because this is the entry number here. Here is the number n, it's off by 1. But 52 is 0. 53 also. And 54, oh, that's an interesting sequence. 3 in a row here. That can't be. Okay. All right, so that is this. And so that's kind of a fun one to check. Let's go back to the board here and look at Lagrange's theorem. So very similarly, Lagrange showed that if we use the square numbers, then we can partition any number into, if we have 4 or more. So that means, that means there are 2 non-trivial sets here. The first set, of course, is going to be the square numbers, and then these 2 sets are going to be numbers that are missing some, not all of the integers, and then S4 would be all of the integers. So let's do what we did over here and see if we can find the sequences that are n minus S3. So let's go back and do that. So I will change this now to square numbers and change this to 3. I think that should do it. So let's look here. First one is 7. So I'm going to type this into here. 7. 15. And what's the next one? 23. 28 and 31. Okay, hopefully I didn't miss any, and it should find numbers that are a sum of 4 but no fewer values. So 7, 15, 23, 31, 52 is in there, so that's our famous 52 here we've been using. But let's see, 60, for example. So 60 should have 0, and we see 0 there for 60. 63 should be 0. So we're seeing that. What's interesting about this theorem, and you can check this out, I won't do it here, but this is neat. All these numbers are of this form. 4 to the I times 8 times parentheses 8j plus 7. And if you work those out, then you'll get these numbers here. So that's kind of an interesting part of Lagrange's theorem. Okay, so this completes the course, the mini course, and lots of things you can do here. It's fun to just explore the properties of these guys and see what you find. If you find something really interesting, share it in the comments so other people who are working through this course can see that as well.